Welcome back. Of course, I don't know whether you actually tried this exercise. You really should. It's worth doing. But just in case you didn't, I'm going to do it for you. Just checking I've got a useful pen. So let me draw a diagram. I've got light coming up out of water, 1.5, into air, 1.0. It comes up. It's going to refract away from the normal. This is the angle of incidence, this is the angle of refraction. Well, the angle of incidence was 48 degrees. Let me just write that in, 48 degrees. Okay, N1 sine theta 1 is N2 sine theta 2. That's coming from water, 1.5 sine 48 is equal to N2 is air, sine R. Well, multiplying by 1 doesn't change anything. So sine R is this, which means to get R, I have to go inverse sine of 1.5, which is my decimal point, sine 48. So give me a moment to get a calculator. Here we go. Inverse sine of 1.5 sine 48 is what? Maths error? What's going on? What's going on is this. The light ray coming in, okay, better go back to here. The light ray coming in tries to refract. But have another look at this value. That value that's causing a problem is 1.5 sine 48. If I just evaluate that, I get 1.1. Wait a minute. Sine values can only go from -1 to +1. There is no angle which has this as its sine. That is to say, there is no angle R that can satisfy this equation. There is no angle of refraction which could possibly work for a light ray coming in water at 48 degrees to the normal. It cannot refract. That means what we've got is something called total internal reflection. The light rays coming at shallow angles to the normal, let me draw in the normal, will refract away from the normal because they're going into air that's thinner. Some of it will also reflect. Be careful. The angle of reflection here, let me get a darker pen. The angle of reflection here is equal to the angle of incidence here. It's got nothing to do with Snell's law. But this angle of refraction is calculated with Snell's law. Okay, a light ray comes in a bit further from the normal. The angle will still refract even further away from the normal, and some of it will reflect. But at a certain point, called the critical angle, the light ray coming in will refract exactly along the surface. This happens, my equation was N1 sine theta 1 equals N2 sine theta 2. This happens when this refraction angle, or rather this refraction angle, is 90 degrees. The refracted ray is 90 degrees from the normal. It goes along the surface. A light ray coming in any further from the normal than that cannot refract because there is no possible angle of refraction which will satisfy this equation. It just doesn't refract. It totally internally reflects. No light is refracted, all the light is reflected. And again, just to reinforce this, the angle of reflection is equal to the angle of incidence. There's no Snell's law here. Snell's law doesn't work. Now imagine this if you're looking at something underwater. You may have seen a picture or a video like this before. The light rays coming up from down in the water hit the surface, and they're so far from the normal that they cannot refract up into the air. They totally reflect, and you get a perfect mirror reflection. I say it's a perfect reflection. It's not a specular reflection because the surface of this water is disturbed by the waves in the water. But the light is totally reflected down back into the water. It's a beautiful effect. So let's look a bit more carefully at that critical angle. Let me remind you where this equation came from. N1, oops, wrong colour. Let me try that again with a lighter pen. N1 sine theta 1 is N2, can move this out of the way, N2 sine theta 2. But here, this angle here is 90 degrees. And if that's 90 degrees, then sine of 90 is 1. So I just have N1 sine theta 1 is N2. Or the sine of the critical angle is N2 over N1, cross multiply. Well, N2 over N1 here is just the relative refractive index. And the most common case is going into air, where N2 is 1. So most of the time we'll have the critical angle is 1 over N, 1 over the refractive index, the absolute refractive index of the material you're coming from. But more generally, it's the relative refractive index.